Today we are going to add a regulator to our filtered power supply. To get started, let's build our power supply up to the point where we had it in the last video. So I have my breadboard here, some diodes, and a capacitor. So let's go ahead and build that up to the circuit we had in the last video. Okay, let's take another look at our breadboard here. So as we build this power supply, I'm going to show you how the breadboard works. We already did the demonstration of the bridge rectifier in the last video, but now I'm going to be taking this to the next few steps. So I want to make sure you understand how this breadboard works. What we have are a number of holes that are 1/10 of an inch apart each, and the connections are such that these 5 holes here are connected together. There's a gap across the channel here, and these 5 are connected together. There is no connection this way along here. So these 5 are connected, these 5 are connected, these 5 are connected. And likewise on this side. So we have 1/10 of an inch centers, which is standard for dual inline package ICs. And so that's convenient for building IC circuits. And so if I want 2 leads of a component connected together, I put them in 2 of these 5 connectors here. So I can have up to 5 different leads into one of these vertical channels, or if you want to call it, if channel is the right word. These are connected horizontally all the way across. Now some of these breadboards have a gap right here, and you have to bridge across to have a connection all the way across. But this particular breadboard is connected all the way across, and so if I put a lead in here, it is connected all the way over to the opposite end, and likewise up here, but there's no connection vertically, so these holes are not connected to these holes, and likewise down here. And for convenience, they gave us some markings here, plus and minus. I don't have to go by those, but and maybe I will, maybe I won't. In this project, definitely won't, because this will be our ground when we're finished. That'll be our lowest possible voltage, and I will designate that as ground. We will have our unregulated voltage up here, and when we build the regulator, we will put the regulated voltage up on top. So let's go ahead and build our bridge rectifier. So here's the schematic for the bridge rectifier. Remember that our cathodes, or the pointy end of the diodes, generally points toward the positive side of the rectifier. Remember, the rectifier is a voltage source, so where the conventional current exits a source is where we have the higher voltage, or the positive voltage. So it will have positive on this side, negative on this side, and then the AC goes to the points as I have here. I prefer the diamond on point drawing for bridge rectifiers, and so that's how we will connect this here. So the AC goes to the top point and the bottom point. Negative is to the left, positive is to the right. So let's go ahead and put this together. So here is a diode, and there is the cathode mark right there. So I want that to generally go to the right. So I'm going to choose to put my anode here. Actually, I'm going to move my anode to this hole. You'll see why in a moment. And I'll put my cathode, I don't know if you can see what I'm doing, but I'll show you in a moment. So here I have the anode here and the cathode there. Why didn't I put them on the very ends? You'll see in a moment. I'm leaving those open for the convenience to put other leads. So notice it's pointing from left to right. So here is another diode, and I will put that I've just made an executive decision to move this over to here, and you'll see why in a moment when I finish the circuit. So I'm going to put this one, once again, generally the arrow is pointing from left to right. I'll put that in that hole. So since these 2 are in the same 5 that are connected vertically, these 2 leads will be connected together, and I will put this one right here. So now I've built the first half, the left half of the bridge rectifier. Now I've left this hole open, and I've left that hole open. You'll see why in a moment. Now I'm going to put the next diode in. I'll put that on the top. I'm going to put that in this hole here. Now these 2 are connected together, and I'm going to put this one actually right there. Now I left that one open for the next diode. You'll see in a few minutes why I left that open. You have to think ahead a little bit when you're building these circuits of where I'm going to put what. So I did put this in that particular hole for a reason, and that will be shown in a moment when I put the last diode in. Let's go ahead and stick this in here. Put the anode right there and the cathode right there. And we're done. So there's our finished bridge rectifier ready to go. Now what I want to do is take my negative side, which will be here, and put that to what I'm going to designate as the ground, which is the top row along here. So what I need is a jumper. I have a kit of jumpers. Here's my dusty old jumper kit. I have all different sizes in here, from jumps across 1. These are in tenth of an inch increments. There's a 1/10 of an inch, 2/10 of an inch, 3/10 of an inch, and so I have different color-coded jumpers to go to different distances on the breadboard. So I've chosen a yellow jumper. I think that's the right length. Let's see if it goes where I want it to go. I want it to go from the negative side down to where my ground will be. Let's see if it'll fit. So I'm going to take it from the closest hole. Oh, perfect fit. Maybe I could have taken one a little shorter, but it's doing exactly what I want. So see now that these 5, let me use this as a pointer here, these 5 holes are connected together, and so I have a diode anode here, a diode anode here, and then this is connected to those because these are all 5 connected together, and I'm jumpering down to my ground along here. So now I have my negative side connected to my ground, and I'm going to take another jumper and I'm going to connect the positive side to my unregulated voltage right there. So there's the positive side of the bridge. These are connected together, and you see I jump it up to what's going to be my unregulated voltage. So there's my bridge rectifier built and ready to go. So these are together, these are together, these are together, those are together. My negative side goes to my ground, my positive side goes to my unregulated voltage. Now let's go ahead and hook up our alternating current. So here is the secondary for the transformer, and that's why I left these holes open. Nice convenient place to put my transformer secondary right there on the point where I like to draw it. And so I'm putting it physically where I tend to draw it in my schematics, and put the other one on the bottom right here. And now the transformer is hooked into the rectifier. Let's see how that looks on the oscilloscope. Okay, let's get this oscilloscope hooked up here. Going to hook up the ground to the negative side of the bridge, and I'm going to hook up the probe to the positive side. And well, that looks a little funky. What's going on there? What's going on is we are expecting to see the wave shape of a full wave rectified sine wave. Well, what's going on is that I'm not taking any significant current through the diodes, and they're not switching on and off correctly. So what I need to do is put a little bit of a load on here. So I have a 1K resistor that I'm going to put across the rectifier to load it down just a little bit. And as soon as I do that, now that looks a little bit better. This particular oscilloscope does not have a line trigger function, so what I'm going to have to do is hook up the oscilloscope's external trigger up to the transformer, which I am doing now. And once I do that, it should stabilize if I get a good connection here. There we go. So now we see our full wave rectified sine wave. So that's what we expect to see from the rectifier. Okay, so the next component to finish what we had already at this point. In our previous video, we had the capacitor filter hooked into this. And I'm not going to use my 8,000 microfarad capacitor. I'm going to use this 1,000 microfarad capacitor. Simply, well, for 2 reasons. One, it's smaller, so it'll fit on this board. And the other thing is, it's really undersized by quite a bit, and it's going to make the ripple in our circuit more dramatic. So when I demonstrate how the ripple comes into effect when we load down the circuit. As you may recall in the previous video, we had a nice unregulated power supply. We had a 16-volt output, but as soon as we started to take current from that, what happened? We not only had the voltage drop as you normally do when you take current from a circuit, but we also had this 120 hertz ripple, because the capacitor would charge slowly, then discharge, actually would charge quickly, discharge slowly, giving us this characteristic sawtooth ripple. And it was a little hard to see with the 8,000 microfarad capacitor, so I'm going to use this 1,000 microfarad to make that a little more dramatic. When we finish the power supply, we'll use a bigger capacitor, and we'll calculate what that capacitance should be when we get closer to the finished project. So I want to put the capacitor from the unregulated voltage here to the ground. So let's give ourselves a little space. There's the positive side. I want to be careful with this. I don't want to put this in backwards, even on purpose to make a demonstration. This thing could pop like a cork. So there's the negative side that will go to the ground. Positive side is going up there, and let's just stick that in there. So now there is our filter capacitor, and now let's see how this looks on the oscilloscope. So there's our about, let's see, this is set for 5 volts per division. So it's 5, 10, about, looks like about 15 volts. We're taking a little bit of current. If I take out that resistor, it should go up a bit. Yeah, it did. So that 1K resistor is pulling enough current to bring our voltage down. So there's no load, just the capacitor. Put the 1K resistor, and that pulls the voltage down just a little bit. So just a tiny bit of current that a 1K resistor takes out of the circuit is enough to load down the circuit and take us down about a volt. So now that we have our original circuit built, let's move on and add a regulator. Right now we have the oscilloscope hooked up to the capacitor, and remember, an oscilloscope is just a voltmeter that shows us voltage over time. So right now I have this set at about a time base of 5 milliseconds per division. That's not really too important right now. We'll see how that works in a little later. But the most important thing is I have my channel A set to 0.5 volts per division. This is a times 10 probe, which means that makes it 5 volts per division. Now I'm going to set the input coupling to ground, and when you have the input coupling set to ground, wherever this line is, that is 0 volts. We go above that line, we're positive. We go below that line, we're negative. And I can use this position to adjust that wherever I want. For right now, I'm going to put that right in the middle. So this is 0 volts. Going up is positive, going down is negative, and it's 5 volts for each one of these major divisions. So I set this back to DC coupling, and what do we have? It goes 5, 10, 15, just about 16 volts. So that's what we have to work with here. Now let's go ahead and load this down a little bit. I'll put my rheostat on there. So I'm putting this on these two connections here. So now I have 100 ohms. I turn this over like that. It's 0 ohms, back over to here 100 ohms, and about 50 ohms there. So I can use this as a load to see how this acts under different loads. And I'll put the black to the negative and red to the positive, although the rheostat doesn't really care. And there we go. You can see some ripple up there. It's going down to about, we can see that we're going up to about 10, 11, 12, 13, about 13 volts and up to about 15 volts. So it brought it down just a little bit. Remember, whenever you pull current out of a system, that system has an output impedance. There's a resistance or other impedance that's always in series with our voltage source if you look at the theoretical circuit. So here we have a voltage source and a series impedance, which is called the output impedance. Whenever you pull current through an impedance, what do you get? You get a voltage across that impedance. And so since this voltage on the left side is unchangeable, if we have a voltage across here and it's positive to the side where the current comes from and negative to the side where the current exits, then we're going to have a lower voltage where it comes out. So that's what happens. As soon as we hook this in, let me unhook it. So it went up to 16 volts, and as soon as I start taking current, the voltage is going to drop. That happens with any kind of circuit. That's because of the current going through the output impedance. And in addition, we have a considerable amount of ripple here, a lot more dramatic than when we had the 8,000 microfarad capacitor in there, but that helps us see what's going on. So we see the capacitor is charging and then slowly discharging, quickly charging, then slowly discharging, as it has very little impedance on the side where the rectifier is, so it charges very quickly, but we only have 100 ohms here, our load is only 100 ohms here, so it doesn't take as much current, so it discharges a little more slowly, so we get this little sawtooth wave here: fast charge, slow discharge, fast charge, slow discharge. If you remember what we have here, we have a full wave rectified sine wave here, and so each time that comes up, we get on the peak, we charge up, and then it discharges, gets hit by the second peak, as we see here in the diagram, as we remember from our previous video. Okay, so that's what's happening. It's unregulated, so we get some ripple and a little bit of a drop in voltage. If I if I reduce the resistance, thereby increasing the load, look what happens. Our ripple gets worse. Now we're going down to about, looks like 12 volts, and up to about 15 still. As I increase the load, now we're going down. Now we have about 25 ohms of resistance, so I've increased the load, and look how we're going up to about 14.5 volts, and then down to about 10 volts. So the more load I give it, the more ripple we have, and the more voltage it goes down to. And if I get down to very, very low resistance here, we're pretty much losing our DC altogether. Something just, there we go. Sometimes you get loose connections here and funny things happen. If you see something funny happen on the screen, probably something came a little loose. These breadboards do that. Okay, let's take this back up to 100 ohms. Well, it got a little warm there. Okay, so what we want to do is regulate this, and there are multiple ways to do this. What we're going to look at first is a shunt regulator. And shunt means a bypass, which means a parallel circuit. What a shunt regulator means is we're going to do something to get a steady voltage out of this and put our load in parallel with that steady voltage. Now, what component do we have that, regardless of the current going through it, is going to tend to give us the same voltage? And that, of course, is a Zener diode. So I have here a 1N4742 diode, which is a 12 volt Zener diode, 12 volt, 1 watt, and it wants about 21 milliamps of current through it. So if we look at the specifications here, zero in on the 4742, we see that it wants 21 milliamps nominally. So if we look at the circuit, how are we going to design this? We have to have our Zener diode. Now remember, the Zener diode is working reverse biased, and that's one of the most common mistakes I see is people will put the Zener diode in wrong and it goes poof very quickly. So remember, we've used the Zener diode reverse biased. So here's our positive, here's our negative, and we have to have a current limiting resistor in series with the Zener diode. The question is, how big is this resistor? If we look at the circuit here, we see we have 16 volts across the whole circuit. We're going to have 12 volts across the diode. So that means we have 4 volts left across the resistor. Remember Kirchhoff's voltage law. The voltages across the components in a series circuit will add up to the total voltage. So we have a total of 16 volts, 12 volts here, so there must be 4 volts left over for that to add up to 16 volts. So we have a resistor that has 21 milliamps going through it and 4 volts. So we need to figure out what resistor we need there. So let's pull up our trusty calculator. We always divide into our voltage, so we have 4 volts, and we divide that by 21 milliamps, so 0.021 equals, so we need about 190 ohms. Well, I'm not going to find that, but I do have a 200 ohm resistor ready to go. So here we have a 200 ohm resistor. It's a 5% resistor, so we have a brown for 2 and then 3 black lines. Probably can't see that. Doesn't matter. It's a 200 ohm resistor. So we're going to put 200 ohms in series with the diode. So let me put this on here. Take a close-up look at what we're doing here. So we want I'm going to put that in the unregulated power at the top and over to here, and now we will put the Zener diode in here. If I can get that to go in. There we go. So now I'm going to hook up channel 2 of the scope to the cathode of the Zener diode, do some push button magic here, and now we have both channels. Let's take a look at how this is working for a moment. Let's set channel 1 to ground. Remember, I set it to ground. Wherever that line is, that's my 0 volts. So my channel 1 0 volts I have in the middle. Set that back to DC coupling. So that's going to be 5, 10, 15 volts. There's our ripple. Channel 2, let's set that to ground. And wherever I put this line is where my 0 volts is. So where's my 0 volts? Well, it's all over the place right now, but I'm going to put 0 volts right at the bottom here. Set that back to DC coupling. Both of them are set to 0.5 volts per division, which with times 10 probes, that means that that's 5 volts per division. So it's going to be 5, 10, 1 volt per minor division, so 11, 12. So there's my 12 volts across my Zener diode. Now I'm not going to put my load across the Zener diode, and I'll explain why in just a minute. To simulate what's going to go on with a shunt regulator, I'm going to just go ahead and put my load same place it was across my capacitor. I'll explain in a moment why I don't put it across the diode, which is where it should be. So the load should be in parallel with the diode, but I really can't with this circuit, and I'll explain why in a moment. But I can simulate what would happen by just putting the load across the capacitor, and I'm going to increase my load, so I'm dropping down to about, well, there's about 50 ohms. It's handling 50 ohms okay. Well, I'm getting just a little bit of a dip. Remember, what happens is if this voltage goes below 12 volts, my Zener diode cannot give me 12 volts. It can't give back what I don't give it. So as long as this voltage stays above 12, this will stay above 12, but watch what happens as I increase the load. That's dropping down below 12 volts, and every time it drops down, we get a little dip. So this goes down below 12 volts, I get a little dip, a little dip, a little dip. So I'm losing my regulation. So whatever that current is that drops me down below 12 volts, that's the maximum current this can give me. Let's go ahead and find out what that current is. Let's set this for current and put it in series with my load. May have gotten that backwards, but digital meter shouldn't care. Yeah, I got it right. So about 260 milliamps. Am I getting some drop? Maybe just a tiny bit. Yeah, let's call it 300 milliamps. So it can just be even numbers. So that's 300 milliamps that this can give me before my unregulated voltage starts dropping below 12. And of course, if I add a lot of load, there's what happens. Let's go back up to 100 ohms and we decrease our load here. So let me explain why I didn't put the load across the diode. That's one of the disadvantages of a shunt regulator. So if we look at the circuit here, we have 16 volts across the diode and the current limiting resistor, and we have 12 volts across the diode. All right, so that 12 volts is also across the load, and that load is taking 300 milliamps. So where's that 300 milliamps coming from? Remember Kirchhoff's current law. If we have a certain amount of current going here, which is 21 milliamps, and another 300 milliamps going here, that current had to come from up here. Remember, the current going out of a node must equal the current going into a node. So whatever comes into this point also leaves that point. So we have 321 milliamps now going through that resistor. So we need to recalculate that resistor. So what we have here, we have 4 volts. Let's put the calculator here. We have 4 volts divided by 321 milliamps. Let's try that again. So we have 4 volts divided by 0.321, 321 milliamps equals, that gives us a 12 ohm resistor now. So we have to change the circuit to have a 12 ohm resistor. No problem. Put a 12 ohm resistor there, and now it will work. But let's take a look at what happens if we remove the load. So look at the circuit here. We remove the load. All right, we still have 12 volts across the diode, 4 volts across the resistor. The resistor is 12 ohms, so we're still going to have that 321 milliamps going through this resistor. And where's it going to end up going? It's going to go through the diode, and it's going to burn up the diode because this diode is not made for this. It's only a 1 watt diode. So we need to have a much heftier diode just in case we remove the load, so when we dump all that current through the diode, if we remove the load, we don't destroy the diode. Of course, Zener diodes are pretty cheap, and I guess we could sacrifice them in such a case, but that's one of the disadvantages to a series regulator, is that you have to have a hefty enough diode so that if you do remove the load, all the current that was going through the load now goes through the diode. The diode needs to be able to take that. So let's look at another kind of regulator. This is called a series regulator. So the idea of a series regulator is we have a resistor in series with our load, and that resistor is smart and adjusts its resistance to whatever it takes to keep the voltage across the load constant. So let's look at an idea here. Let's say we have 10 volts to begin with. We have two 5-ohm resistors. Our load is 5 ohms and our regulator resistor is 5 ohms. That's going to give us 5 volts across the load. Now let's see what happens if we increase the load. When we increase the load, that means we're decreasing the resistance. So let's decrease the resistance down to 2.5 ohms. Well, the regulator resistor will adjust its resistance to also be 2.5 ohms. And now Kirchhoff's voltage law says we have 2.5 ohms here, 2.5 ohms here, two equal voltages. So we have 10 volts, 5 volts here, 5 volts there. And now if the load decreases, meaning the resistance goes up, so let's take that back up to 5 ohms, well, now that's going to want to increase the voltage, but the regulator resistor will increase its voltage to 5 ohms so that it will keep the voltage the same. So now we still have 10 volts, two equal resistances, 5 volts here, 5 volts there, and as long as we keep changing the load, this resistor will keep changing to keep the voltage constant. So how can we make that? Well, it's very easy to make. I'm going to do it with this transistor. This is a TIP31 transistor. It can handle 3 amps of current, which is pretty much ideal for the circuit we're working on. I'm designing a 4 amp power supply, but I tell you the truth, I don't think it's going to handle more than 3 amps realistically. So this is the perfect transistor. So what we need to do is put the Zener diode cathode to the base of this transistor. So what's going to be on the emitter? Remember, we always assume that the base to emitter voltage of a silicon transistor is going to be 0.7 of a volt. So if we have 12 volts at the base and we have, that's going to be the higher voltage, the lower voltage will be on the emitter. So we have 12 volts on the base, we lose 0.7 of a volt, so we have 11.3 volts on the emitter. And regardless of the current, we increase the current, it's still going to maintain very closely that particular voltage. So let's go ahead and put this in here. I want the collector to go to the unregulated voltage. So here's the base, the collector, and the emitter. So the collector will go to the unregulated voltage, and at this point we'll just have the base and the emitter just sitting here where we can access them. Now I need to let's get this out of the way here. And I'm going to put the cathode of the diode to the base of the transistor. The collector is going to the unregulated voltage. So now I'm going to put my probe on the emitter, and there's our 12 volts. Now I can actually put our load on the emitter of the transistor. I'm going to take this off just so I can clip the load here. And I'm going to move this over to here. Let's see, it's the red lead. So if I hook this up here, can you see what I'm doing there? I'm hooking it up to where the red lead's coming off, so that will be to the same voltage. We're just here's the lead going over to here. There's our probe from the oscilloscope. So there's our output voltage, and now we really do have the load across the emitter of the transistor. So this is a finished regulated power supply. It's not perfect, but we'll be making a more perfect one later. Let's increase the current and see what happens. So as we increase the current, I'm increasing the load down to about 75 ohms, about 160 milliamps. Working good, working good. As long as this does not drop below 12 volts, we should be good to go. And 210 milliamps, 250, about 250 milliamps, we're starting to lose regulation. If you look real carefully, you can start to see the little dips here as these drop down below 12 volts. And if I increase it a lot, we get a lot of loss in regulation, so we've gone beyond what it can handle. So it can handle about 250 milliamps. What can we do to increase that? Well, to get more current, we'd have to get a heftier transformer and a bigger capacitor. In fact, a bigger capacitor would help right here, but I wanted to make this a little more dramatic. Now, I'm actually designing a 3 amp power supply, so I'm going to need a much bigger capacitor there, but that we will worry about later. So there is your series regulator. Now, it's not perfect, If we look really closely, as a matter of fact, let's put this back in voltage mode here. Take it out of the circuit. And what we're going to do is look at the output voltage with the voltmeter, because we can see that a little better with the digital meter than we can with the oscilloscope. I'll put that on the anode of the Zener diode. Anywhere along the ground I can put that there, and I'll put this on the output, which is right here. So there's 11.82 volts. Now let's see what happens as I increase the load. 11.82, 81, 80, 79. So notice my voltage is going down slightly. It's you can't really see it on the oscilloscope, but we can definitely see it on the meter. So I decrease my load and it goes back up. So 11.81, and I go down to my 250 milliamps and it drops down to 11.71. That's probably good enough. But if you need more precision, you need a precision regulator, and that's what we're going to do in the next video, is to add an operational amplifier to this to make a precision regulator. And we'll add some other things too to make the finished circuit. If you found this video useful and informative, please give me a thumbs up down below. It really helps the channel. And subscribe, because that not only informs you when I put new videos up, but it really helps the channel also. And a big thank you to my patrons at Patreon. I could not make these videos without your support. If you want to help me put these videos online and keep real vocational education free at vocademy.net, you can go to patreon.com/join/vocademy and pledge your support. And again, a big thank you to my patrons who make this possible, and a big thank you to everyone for watching.